Hello and welcome back to my YouTube channel, the place where you come to understand about optimization, applied maths and scientific computing. So today we are going to deal with a very interesting topic called Gauss-Legendre. So let's get started. So basically Gauss-Legendre formulas are a set of nodes and weights that you can use to integrate polynomials exactly. If you have an n-point Gauss rule, you can exactly integrate 2n minus 1 order polynomial. In this video, we'll quickly discuss about what are the core fundamental numerical techniques available and why Gauss quadrature is better than them, then the underlying principles, then we'll do the derivation of the nodes and weights, then I'll quickly show you an example over MATLAB, and then we'll do the accuracy comparison. The most basic numerical integration method is the Reimann sum. So let's say I have a cubic polynomial described over the domain from -1 to 1, then the exact integral will be 0.8. To integrate it numerically using the Reimann sum, so we'll take the function value at the left end, then multiply it with the distance that we want. So let's say if I divide the whole domain into 4 parts, so my del x will be 0.5 and the height will be corresponding function value at the left end. So if I do the sum, I'll get a Reimann sum. And here you can see that the error is large. A better technique would be to use trapezoids. Again, we'll take the function values at both the nodes and then use that to calculate the sum. Here you will see that there is a much better agreement between the values of the exact integral and the numerical calculated value. And clearly, with an increased number of divisions, we can get to a much better value. To assert on this point, we have performed the Reimann sum and the trapezoidal sum over a varied number of intervals, and the results are as follows. Clearly, when we are using 32 intervals, the error is much smaller in trapezoidal integration. But 32 points are quite a lot. So we sit back and ask the question that can we be smarter? Can we perform the numerical integration with the same accuracy with much lesser points? So instead of using equally spaced points, can we use some special points and weights? And then can we get the exact results with a much lesser evaluations? So the traditional thought process was to use equally spaced points, but we can do smartly and choose a few carefully chosen points which can have better accuracy. So this is the idea behind the Gaussian quadrature. So there are some basic rules that needs to be followed while deriving the Gauss-Legendre points for doing numerical integration. So first is the Gauss points needs to be symmetric and the weight should be equal for those symmetric points. Then all the weights must be positive and the sum must add up to 2. Then an n-point rule must be exact for a polynomial up to degree 2n minus 1, and no endpoints will be used as Gauss points. So now let's quickly derive the Gauss quadrature formula. So for the 1-point Gauss rule, it should be able to exactly integrate up to linears. So first we'll integrate those linears from -1 to 1. Then we'll get the result as 2b. For a generic linear polynomial ax plus b, the integral is 2b. By Gauss rule, it will be w1 times the integrand value at x1. So now we'll just equate the coefficients of the linear part and the constant part to figure out what is w1 and what is x1. So here we can see that w1 is 2 and x1 is 0. Similarly, we'll derive the 2-point Gauss rule as well. So again, integrating a cubic polynomial from -1 to 1 and using a 2-point rule. So there will be 2 evaluations which needs to be equal to this integral value. Again, taking a generic cubic polynomial and equating the coefficients of different powers, we get 4 equations. And applying the rules of symmetry, we can say that w1 will be equal to w2 and x1 will be equals to -x2. Applying these conditions, we will figure out that w1 and w2 will be 1 and x1 and x2 will be minus and 1 positive 1 by root 3 respectively. Now for the final derivation, we will do a 3-point Gauss rule derivation as well. So a 3-point Gauss rule will be able to exactly integrate a polynomial of up to order 5, and it will use only 3 sample points. So now again equating the power terms, we will get there are 6 equations in total. And then again that W1 and W3 needs to be the same, and X1 and X3 needs to be symmetric. So X1 will be equal to minus X3. Applying these conditions, apart from the 6 equations already given, we will solve to get the following values. That W1 and W3 will be 5 by 9, W2 8 by 9. Similarly, X1 will be minus 3 by 5 square root, X2 0, and X3 will be positive root 3 by 5. To summarize, we can put in that for 1-point Gauss rule is able to exactly integrate up to linears, and the corresponding weights and quadrature points are given here. Similarly, 2-point Gauss rule is exact for cubic, and 3-point Gauss rule is exact up to 5th order. So any n-point Gauss rule can exactly integrate polynomials of up to degree 2n minus 1 exactly. But now you will ask the question that can it be used for an arbitrary integration domain from a to b, because all the derivation is done from minus 1 to 1. So to show that, I'll plot a function which is a constant from domain minus 2 to 4. Then I'll do a linear map from a to b to minus 1 to 1. With this linear map, we can store it that information that how that mapping is performed and how much scaling needs to be done into integral value. So once I plotted the function in the master space, then I'll do the integration separately for the original function in the original domain and the mapped function in the master domain. So you will see while doing the hand calculations that they differ in a ratio of 3. That 3 is the Jacobian. That Jacobian is nothing but the partial derivative of the mapping. So this stores the information that how they are related. So in conclusion, we can say that we can always put a function in any arbitrary domain, map it to a master domain, then integrate in that domain, multiply by the Jacobian value to get the integral value of the exact function over the exact domain. Now you will ask me the question that whether we can perform integration of some special functions. So to that, my answer is that any special function can be represented as a series sum. By this example, I am showing that e to the power x can be written as a sum of monomials. This monomials, as we know, can be exactly integrated using the Gaussian quadrature. And since these are a very good approximation to the exact function, so the integrals will also be exact for that particular polynomial approximation. So in total, we will be very close enough to the exact value. There is no point in studying theory if we can't apply it. So to apply it, I have written some MATLAB codes which you can download from a GitHub page. There will be 5 functions in total. There will be 4 live scripts. And then this LGWT function, which is available on MATLAB Central, which I have imported, that calculates the Gauss-Legendre nodes and weights for any n rule, so that you don't need to calculate those n points manually. Now I'll quickly explain you the basics of my code. So you have a function definition and a domain definition. Then you integrate it exactly using the inbuilt function of MATLAB so that you get an idea of the error. Then you divide the domain into sub-intervals of equally spaced rectangles. Then you multiply those heights by the width of the rectangle to get the area of one rectangle. Then you add it up to get the total Reimann sum. Here I have used the midpoint rule for the Reimann sum. So I'll just give it a run once. So on the right, you can see the output. You'll see that as the number of rectangles are increasing, the errors is decreasing. So I'll just quickly increase the size of the result so that you can see it more clearly. So if I'll just export it from here, you'll see that the final error is of 10 to the power minus 3. So with 8 points, with 8 function evaluations, we can go to an error of 10 to the power minus 3 using the Reimann sum. So I'll quickly run it once more so that you can see how the error is decreasing. So here you can see with n is equals to 2, the error is of order minus 10 to the power minus 2, and it is slowly decreasing till for n equals to 8, I go to an error of 10 to the power minus 3. So if I now increase the points from 8 to 15, remember this is a Reimann sum. So Reimann sums tend to be less accurate. So even with the number of function evaluations going up to 15, I'll still be able to get a decent error of 10 to the power minus 3, which I want to avoid. So to perform it better, instead of using a Reimann sum, I'll now quickly go to the Gauss-Legendre. All the framework remains the same as the last function. The only difference is now we are summing up the area of integrals at some special points with some special weights. So now all the rectangles won't have the same width. So now I'll quickly just give it a run from 1 Gauss points to 8 Gauss points. So here you'll see in the right, as the number of Gauss points go beyond 4, the error is less than 10 to the power minus 6, which is a huge change with respect to the Reimann sum. So again, what I'll do, I'll just rerun it only for 3 Gauss points. So if I start with only 3 Gauss points, I'll see that the error is much smaller than a Reimann sum of 15 points. So in total, you can see that even if we are 100 times more accurate, we are using only 5 times less the number of function evaluations. So in totals, we can say we are 500 times efficient than the normal traditional Reimann sum. This is the power of Gaussian quadrature, and I hope you learned a lot about it today. So please download the course from GitHub and start playing it with yourself and understand it a bit more while exercising on different functions. So I'll see you again in the next video. Till then, please show your love by liking and subscribing. Thank you.